All right. Hello, everyone. Welcome to my talk this year at Lambda Jam. It's great to be back at Lambda Jam. I'm George Wilson, and this is Cultivating an Engineering Dialect. This talk's about Haskell, as you may have come to expect. All my talks are about Haskell, or at least most of them. And this one's about Haskell as well, but this isn't about a new algebraic gadget that I've been thinking about that I think you need to know about. This talk's instead about some engineering concerns that a team or a business adopting Haskell will need to take into consideration. I'm going to tell you about a problem. It's a pretty big problem, and I think Haskell is particularly susceptible to this problem. It's a problem that's not unique to Haskell, but Haskell is particularly susceptible. So I'm going to describe the problem to you. I'm going to show you the proposed solutions that already exist, and then I'm going to propose my own solution. So I'll start off with an instructional parable. This is an example. It's going to start off really beautifully, but it will end in catastrophe. So let's start off beautifully. I want to think about learning functional programming, learning Haskell. It's like riding this wave of knowledge and learning and all these incredible ideas and all this wonderful stuff. You know, there's always, it's not like learning. There are lots of programming languages where I sort of learn them and then all my skills transfer and then I just do what I was doing before. But with learning Haskell and FP, there's all these amazing libraries and language extensions and architectures and all this incredible stuff, this rich history. And we're just riding this wave of knowledge. You know, there's all this stuff. There's parametricity, there's monoids, there's monads, there's monad transformers, there's property-based testing, lens, MTL, the free monad. You know, there's extensible effects, there's recursion schemes, there's functional reactive programming, there's template Haskell metaprogramming, there's generics, GADTs, data kinds, constraint kinds, quantified constraints, Rankine types, dependent types, linear types, you know, type families, type in type, and laws. Right? That's a lot to learn. And it's just so incredible to learn all this stuff and how all these things fit together in this incredible journey. And underneath this wave, there's an undercurrent. And the undercurrent is, you know, you're thinking to yourself, like, one day I'm going to use this at work. One day, like, someone's going to pay me to use all of this incredible stuff. And then one day it happens, you know, one day you join this Haskell team or you form a new Haskell team or you build a startup with 4 people in Haskell, you know, however it works, you end up with this Haskell team and you say, finally, I'm going to do all this stuff, you know, and then there's probably a couple of people who know Haskell really well at the company. And the reason I make that assumption that there are a couple of people who know Haskell really well is if there weren't, you wouldn't be using Haskell, right? So there must be, right? So you've got a couple of people who know Haskell really well. And then you're in the lunchroom. Remember the lunchroom? Maybe you're somewhere else. And someone says, hey, I was learning this incredible stuff on the weekend. I just learned about free monad. I think we should use free monad. And the other Haskell expert in the room is like, oh, that's an incredible idea. That's amazing. Let's ship it. Let's go free monad, you know? And so you'll start to build all these projects over time. You know, maybe you start with a microservice. The boss comes in, he says, all right, team, we need a microservice. And so on this first project, we're using some fairly simple stuff. You know, we're going to use monad transformers for our architecture. We're going to have all these functions and types and type class instances. We're going to build with Cabal, and we have a pretty good time. And we deliver that microservice, and then the boss comes in and they say, all right, that was good. And now I need you to write a command line application for talking to that microservice. And we say, hey, no problem. In fact, we've learned some more cool stuff, right? So the next project, we're using finally tagless for our architecture. We're using type classes everywhere. We love type classes, right? We're going to use so many type classes for everything. We're going to use Stack for our build. We didn't like Cabal. The docs weren't so good or whatever. And we're using Stack this time. And you know, we're going to deliver this command line application. We deliver it. It's great. And what happens next? The boss says, guys, we need another microservice. We say, great. I have just the thing for that. This time, I watched this talk by George Wilson. He said to use MTL and classy optics. We're going to use MTL and classy optics. We've just discovered lens. We're going to use lens for everything. Lens is amazing. Lens is the answer, right? Stack wasn't cutting it. We have to use Nix, right? We're going to use Nix for our build. We're going to use all this stuff, you know. And by this point, your language extension list is looking a bit like this. And right, and then the boss says, all right, that's great, but now we need, you know, another microservice. And you're like, all right, finally, you know, we've been learning even more cool stuff. This one, we're going to use extensible effects. Van Laarhoven lenses are not enough. We need profunctor optics. We need the real stuff, right? We've got type families and GADTs everywhere. Haskell packages in Nix wasn't doing it. We need Nix, Haskell.nix to upgrade our Nix build, you know. We've got all this incredible stuff. It's everywhere. And the boss is like beginning to fear us at this point. Like we're like, you know, beginning to wear robes to work and all this sort of stuff. And the boss says, all right, can you guys write another microservice? And we say, yes, finally, we're going to write the entire service at the type level. Haskell won't do. We're switching to Agda. And now we can transcend reality. All right, what happens next? We've got all this code. We've got this Agda service. We've got all this different Haskell stuff. What happens is the boss says, hey, I need you to add a new feature to project number 2. And you sort of scratch your head and you go, oh, yeah, what's this? This is finally tagless. Yeah, I remember that. Oh, we use too many type classes. This is like, most of these don't have laws. We shouldn't have done it that way. And I don't remember how stack works. Oh, I'm going to have to go and learn it again. You know, right. And so we kind of slow down. We have to load so much stuff back into our heads. And the boss says, hey, there's a bug in project number 3. And then we're like, oh, project number 3. Oh, we're still using Van Laarhoven lenses. I like profunctor optics, but all right. And, you know, I don't remember how MTL and classy optics work. And so what happens is our maintenance has kind of slowed down to a halt because we've just used so many different techniques all over the place that like we just have to load so much stuff back into our heads to work on any of the code. Like we've got this enormous incoherent code base, right? And then, you know, maintenance is slowing down, feature delivery is slowing down. So the company does what all good companies would do. They take our small team and they hire some more people, right? And this is where things really start to go wrong because we've built all of this stuff. It's all so complicated and so incoherent, right? That these new people, they have no hope of coming up to speed on everything they need to do their jobs, okay? Because your code base has a learning curve, right? I love this image for demonstrating that, like this kid with the skateboard ramp and he's on his little bike. This kid has like no hope. His bike doesn't even have pedals, right? So he's going to be like running like Fred Flintstone to try to get up. And he's never going to get up that skateboard ramp, you know? And that's your code base, right? Because, you know, if you're not intentionally building a learning curve, you are unintentionally building a learning cliff. This was an idea introduced to me by Ken Scambler, the learning cliff. You know, we have the beginner down at the bottom here, you know, and then this sheer cliff, this cliff face, this rock wall. And up on top are all our like crazy people, you know, they're talking in maths, they're buzzing like a fridge, whatever it is they do up there. And like all the beginners are just like stuck at the bottom and they're like, well, there's no way I can climb that rock face. It's impossible. And this is game over, right? This is the end of our tragedy. At this point, the business fires everyone, rewrites everything with enterprise Java beans, or even collapses entirely, you know. And so that's a doom and gloom kind of scenario. But this problem exists at many different kind of intensities, right? Even if this doesn't kill your company, you may be feeling this a little bit already, right? You may be feeling this kind of thing. So how can we do better than that, right? We don't want to just have all this incredible complex stuff everywhere that's impossible to load back into our heads, impossible to teach to new people. We've got to do better. And so there have been some solutions that have been proposed already. I'll tell you about them. So some proposed solutions to this problem are the Simple Haskell Initiative and the Boring Haskell Manifesto, which was published by Michael Snoyman. And these two documents essentially say similar things, but they say that what you should do is you should stick to the basics. You know, Haskell comes with all this incredible stuff like algebraic data types and functions and immutability and type classes. And you should stick to the basics, and they'll see you through, and you'll be able to do what you need to do, and you'll have a good time doing it. I find that this approach is a bit sort of reductionist, you know, as opposed to our maximalist Haskell explosion of novelty. We've instead got this sort of contraction going on where we're sort of, you know, previously we were just sort of, whenever we had the opportunity to use a new tool that was really cool and shiny, we just sort of unthinkingly said yes, right? We just said yes to everything that came along. So this approach is the reverse. It says we should unthinkingly say no. And I don't think it's as good a solution as the one I'm going to propose to you. I like to look at this in terms of sort of this idea of a power to weight ratio. The intended target audience of this talk is engineers. So I say power to weight ratio. But if the talk were intended for managers, I would say cost benefit analysis. Anyway, so the power to weight ratio. Before, you know, we were searching for all this power. We were just grabbing as much power as we can get anywhere we could get it. We just need all this power. You know, it was like this quest for novelty. But we were ignorant of the weight that came with all that power, because the weight, it turns out, is in maintenance. And the weight is in bringing new hires up to speed, right? That's the weight, and that's not immediately obvious, right? I think the simple Haskell approach of sticking to the basics is very good for avoiding all of that weight, right? It says, don't pick up any of that extra weight. You don't need it. But I think they're leaving money on the table, right? I think some of that power could be used for tremendous good. And so I have a proposed solution. My proposed solution is make intentional decisions informed by your problem domain, and do so as a team. So what do I mean by that? By intentional decisions, I mean like think hard about it. Whenever you come across some new thing, you should think like, oh, is that going to actually solve the problems I have in front of me? That's what I mean by informed by your problem domain. I mean, you should use the tools that give you a lot of power for the problems you're actually solving, for the problems your team exists to solve, for the problems your business exists to solve. You should use the tools, you should commit to the tools, right, that give you good solutions, the best solutions to these problems. And you should do so working together as a team. And you also need to build a learning curve, right? You need to intentionally build a learning curve onto your team, onto all the knowledge required, so that you can use the best tools available to solve the problems you have. So I'll tell you some more about this. I'll need to tell you a bit about my problem domain in order for me to give you examples that make any sense. Because if I don't tell you my problem domain, then the decisions won't make any sense with respect to the framework I'm describing. So I work for this company, PaidRight, and we're helping Australian businesses to pay their employees correctly. And this turns out to be difficult. And the way that we're doing that is we have these data analysts, and they're reading these legal agreements. You know, it took every fiber of my being not to say laws, but they have these legal agreements, these documents, whatever it is, enterprise bargaining agreements and so on. And they convert those documents into rules in our reasoning engine, right? And then data comes in, and that might be like pay records and timesheets and so on. And then that gets crunched through the reasoning engine, and then results pop out. And we use these to determine, you know, what employees should have been paid in certain pay periods and whatever. And if you're anything like me, and you're looking at this diagram, you're saying to yourself, oh yeah, so we've got this box, right? And data comes in the top and results come out the bottom, and we need a whole bunch of rules to configure what the box does. That's called programming. That's a programming language problem. And indeed, a lot of the problems that we're facing, a lot of the problems that I'm sort of solving day to day have a sort of programming language shape or flavor to them. And so we've decided to use some tools that are very well suited to programming language shaped problems. At a high level, one such tool is Haskell, right? But even the tool selection within Haskell, we're informed by this problem domain. So for example, we are using GADTs. I remember this was kind of the first thing that came up that started this whole discussion for us. but someone used GADTs in a pull request, and that was kind of a new one in the code base. And we said, oh yeah, GADTs. And we had a little conversation like, oh, should we use GADTs for this? Right? Should we, could we do it without GADTs? And we changed the code around to see what that would look like. And it turned out it would be a pretty big pain. And then we sort of decided fairly easily, like, yes, GADTs are the way to solve this problem. And furthermore, like, if you look at all the blog posts or whatever about GADTs, all the blog posts and conference talks and whatever, like their example is always a programming language thing. It's always like, oh, we've got ints and bools and we want to add them and stuff. And so it was a fairly obvious choice for us. And these decisions amortize over time. Like it's very likely that we're going to be using GADTs again, or that they're going to come up again as the obvious and best solution to whatever problem we're facing. And we're building a learning curve, right? So we've got this engineering handbook. And in that handbook, we have a section for all the Haskell stuff we're using that you might not have come across before. And in the handbook, we've got a GADT section that says, here's what you should read to understand GADTs. And we link to the GHC manual because it has a perfectly fine explanation. We didn't need a third-party blog post. So here's the resource, right? And then here's who you should talk to after you've read that, right? If you've got more questions, here's the person on the team who you should talk to. You know, I remember when I sort of started my first job, you know, I was hacking away, and whenever I came across something I didn't already know, I would ask the team lead, and the team lead would say, oh, that's called cake pattern or whatever. Go and find a blog post about that. But the problem with this approach is that the beginner who needs to learn is precisely the person who isn't well suited to determining which of the 10 blog posts is the good one. The people who wrote the code that uses the cake pattern probably know which cake pattern blog post is the best one and the one that works, right? And so we link resources that we think are the good resources for these problems. And yeah, and then we say like, and then after you've read that, go and ask Isaac. Like he does GADTs all day. Like Isaac will tell you everything you want to know about GADTs. And so we give resources and we try to act as a sort of community, all right? I'll give you another example of something that we chose to adopt after a conversation, which is a thing called plated. So at the heart of our system, we have a data type called rule, and rule is very big. It's got 45 constructors, and I couldn't fit them here on this slide, of course. And many of these are recursive. So many of the constructors for rule have rules within them. And we needed to write find and replace on rules to change some names of stuff and that sort of thing. And what we ended up using was this thing called plated from the lens library. With 2 lines, we were able to say instance plated rule where plate equals uniplate. And that just gave us find and replace. But we're paying a cost for this. There's some weight associated with this power. The weight is that now we're going to have to teach anyone who joins the team enough lens to use plated. Now, we're not going crazy with lens everywhere. Like most of the lens we've got is kind of here doing this plated thing. So we're kind of limiting the scope to some degree to give us an easier time. But, you know, but what you can't see on this slide is that above the plated instance, I have this enormous comment that's like 50 lines long that says, here's what plated is, and here's where it came from originally, and which is Neil Mitchell published the original Uniplate and a blog post alongside with it. So we say, you know, here's where plated came from. It used to be Uniplate. We link to the original Uniplate blog post. We link to the plated implementation in Lens. We say, you know, here's the business problem we were solving when we chose to use this. And so now we've got it, and here's what it's good for. And it also links to the engineering handbook section on Lens, right? So like we're just providing people with ways to, when people come across things that they haven't seen before, there should be a big explanation, and then it should link to the relevant blog posts and say, talk to George or Dave or whoever. And that's how we're doing it. So, but again, this decision amortizes because plated is very likely to come up again. We were using it for find and replace, which is kind of the most basic thing you could use plated for. But plated is also useful for, we want to use it for optimizations and simplifications of rules. And by using plated, like we just have that as well when we need it. It's already there for us. So I think this will give us more power over time, and we were already happy. Because if I were going to write find and replace and I weren't going to use plated, then I would have reinvented a weaker version of plated. That's entirely fine. That's okay. You're allowed to reinvent, like nearly everything everyone does is reinventing a weaker version of something else, right? That's entirely fine. But it would have been hundreds of lines of error-prone Haskell code, which I don't want to write, and I don't want to maintain. In terms of the weight that comes along with this decision, I would much prefer the weight of teaching someone Lens. And I have a lot of resources and so on to do that, to help me with that. But it's not all about, saying yes and using things. I'll tell you about how we do database access. We're using a library called Traction, which is really basic. Traction's really basic. Everyone in the room can already use Traction. It's a wrapper around PostgreSQL simple. It's a very thin wrapper. And you just write your SQL queries in your Haskell code. And then it does all the right, escaping and sanitization and stuff, right? And you just write your SQL queries. Haskell has unbelievable, incredible SQL libraries for doing like these little type-safe composable query chunks, right? I really encourage you to go and learn about those, right? Like Opalai or Beam or whatever. But our problem isn't very database heavy. Like we're using a fairly simple sort of like database setup. We're just doing a couple of joins and all that sort of thing. Like we really don't need the all singing, all dancing algebraic composable solution in this case. And I don't want to teach it to anyone. And anyone we hire like already knows how to write SQL probably. And so this was a really good decision for us in terms of minimizing weight, and it's got all the power we'll ever need. Another example is someone made a pull request that used dependent map. That could be a whole talk on its own, but dependent map is, it's a dependently typed map. So you've got keys and values, right? And it's dependently typed, meaning the value of the key determines the type of the value at that key. And it does this with all this crazy GHC constraint stuff. And it's extremely cool. You should go and learn about dependent map. But we were using it in a test, and it made that test much nicer and easier to write. But at the end of the day, it totally wasn't worth, we had a conversation and we said, like, it isn't worth having to teach or explain dependent map to a beginner to make this test nicer, right? And so we ended up deleting dependent map. The test became like 3 times as many lines of code, and that's fine, right? When I went to look for a dependent map blog post, there wasn't one. So I would have to just link to the docs themselves. There was one conference talk on dependent map, but I wouldn't recommend it to beginners. And so I really didn't have a way to build a good learning curve up to this thing in a reasonable amount of time. And it really didn't give us a huge amount of benefit. I'm not against dependent map, right? Someone else solving a different problem will build their entire business on dependent map. Dependent map will be at the heart of everything they do, and their business will be the better for it, right? But that's not the problem I'm solving, right? And it's really important to make these decisions with respect to the problem you're actually solving. So that's the end of the talk. Make intentional decisions, build a learning curve, right? Make these intentional decisions by thinking like, what problem am I actually solving? Use the things that solve the problems you're actually solving, solve them dead, and build a learning curve after you, right? Establish like an employee handbook or something, right? Provide all the good learning resources, all the materials, and say, oh, if you didn't understand the blog post, you can go and bother George, or whatever it is, and so, yeah, I think that's it. That's the end of the talk. Thanks for listening.